Welcome to this explainer. Look, today we're cutting right through the shiny marketing promises surrounding battery energy storage systems, or BESS for short, to get to some pretty harsh operational truths. If you're an asset manager, an engineer, or really anyone working closely with grid infrastructure, you've probably stared at a battery's spec sheet and wondered, how does this thing actually hold up over half a decade in the field? Well, you're in the exact right place. We're going to break down exactly what happens when theoretical data collides with real-world grit. I want to start with this quote from our source material because it just hits the nail on the head. A pristine spec sheet can sell a battery system, but it won't keep it running in year 5. Day 1 of operations, that is basically a honeymoon phase. The financial math totally checks out, the theoretical limits look amazing, and the hardware itself is literally sparkling clean. But fast forward to year 5, and it is a completely different ballgame. The true test of a system isn't how it looks on paper during procurement. It's how it handles the relentless, compounding grind of actual day-to-day grid operation. Section 1. The spec sheet illusion. To understand why this massive drop-off happens, we really need to start by calling out a very common industry trap, and that's the illusion created by perfect data sheets. See, theoretical laboratory performance is calculated in a vacuum. You've got engineers running tests in these ideal 25 degrees Celsius environments, doing perfectly balanced and predictable charge and discharge cycles with absolutely zero external chaos. But actual operational reality? It is messy. It's totally unpredictable. Out on the real grid, you are dealing with 40-degree heat waves, freezing winter nights, and this ever-shifting electrical demand that demands way more immediate flexibility from these systems than a highly controlled lab test ever could. So, the crucial takeaway here is that a massive chasm exists between what is sold on day 1 and how the system actually performs in the wild. By the time you get thousands of hours into the life of that asset, those initial datasheet metrics, they often bear little to no resemblance to your actual asset availability. You might have bought a system that promised an incredibly high percentage of uptime, but the physical wear and tear in the field inevitably starts telling a much more sobering story. And that gap between the marketing promises and operational reality, that is exactly where margins are lost and maintenance budgets are completely blown out. Section 2. Year 5 Operational Stressors. Over time, this huge disparity between the spec sheet and reality is really driven by 3 primary operational stressors. We're talking about thermal management degradation, auxiliary load friction, and environmental wear. Now, these aren't just minor inconveniences. These are the core physical hurdles of energy storage efficiency. And if they aren't aggressively managed, these 3 factors compound year after year, which ultimately drags down the total capacity and the availability of your entire installation. You simply cannot ignore the physical toll that constant thermal cycling takes on these machines over a 5-year lifespan. Think about it. Heating up during a high-demand discharge, cooling down, heating up again, day in and day out. This constant expansion and contraction puts an incredible amount of stress on the physical components of the battery modules. And, well, let's not forget cooling system maintenance. Keeping those temperatures tightly regulated requires active mechanical cooling, usually liquid or some sort of advanced HVAC system. But those cooling systems are mechanical assets themselves, and they become a massive point of failure if they aren't rigorously maintained. Because if your cooling degrades, your battery degrades. And honestly, fans and pumps really don't care what your day 1 spec sheet says. Then you have to add in the harsh external factors. When the dust settles, literally, and fluid degradation sets in, that original datasheet goes completely out the window. Real-world grid demands are not perfectly smooth, predictable sine waves. They are erratic. They require sudden spikes and rapid drops in power. When you combine that unpredictable electrical strain with physical dust clogging up heat sinks, moisture sneaking its way into enclosures, and coolant fluids chemically breaking down over time, well, you can see exactly why year 5 looks so vastly different from day 1. The environment just relentlessly attacks the system. Section 3. Strategies for long-term reliability. So how do we bridge this gap? We've got to shift our focus completely away from those initial marketing promises and move toward actionable engineering solutions. Moving past the brochure means relying entirely on rigorous engineering truth. Actually bridging the gap between laboratory theory and operational reality requires long-term engineering validation. You have to accept that a battery energy storage system is absolutely not a simple set-it-and-forget-it appliance. It's a highly dynamic, heavy industrial asset, and it needs proactive lifecycle management. You just have to validate the performance with real data, year after year. By deploying 3 very practical engineering and maintenance audit strategies that target those exact stressors, you can finally ensure long-term asset reliability. First, you must routinely audit your thermal management degradation. Basically, do not assume the cooling system works like it did on day one. You need to measure its actual efficiency. Second, assess auxiliary load friction. Ask yourself, are your pumps, chillers, and fans drawing more parasitic power than they used to just to achieve that exact same cooling effect? Because if they are, that's a massive red flag that is eating directly into your profitability. And third, relentlessly monitor environmental wear. You've got to stay ahead of the dust accumulation, the moisture intrusion, and the fluid breakdowns way before they cascade into a critical system failure. Active, persistent auditing is really the only way to protect your investment. I want to leave you with a final, slightly provocative question from our sources to really help you evaluate the true long-term viability of your own assets. Engineers and asset managers, how do your actual availability metrics in year 5 compare to the original manufacturer projections? Seriously, take a hard, honest look at your real-world data this week. Compare today's operational telemetry with that pristine spec sheet you originally purchased. The answer you find might just change how you approach your entire maintenance strategy moving forward. Thanks so much for joining me for this explainer. Stay curious and always keep digging for the engineering truth.